In the previous video, we looked at the concept of moments, and we said that a moment is any measure that describes the shape of a probability distribution. And all moments are actually expected values of a function of our random variable x, or the random variable that you're interested in, right? So now in this video, we will look at the concept of moment generating function of a discrete random variable. The definition says the moment generating function, MGF, of a discrete random variable x is defined to be, we'll use the function here, mxt, which is equal to the expected value of e to the power tx, and by definition, expected value of anything within the brackets is equal to the sum over all possible values of a random variable of the product of whatever's in the bracket. In this case, is e to the power tx times the probability of the possible values of x. So we will say that the moment generating function exists if it is defined for an interval of numbers that includes 0 as well as positive and negative numbers of t. So the moment generating function must exist if this summation, if you can calculate or the summation for any t that's between negative infinity and positive infinity, including t equal to 0. So the properties of the moment generating function says the moment generating function exists if it's defined for any t, negative t or positive t, or any t that's between negative infinity and positive infinity. All right. And the moment generating function we'll say exists if when you substitute t equal to 0, then the moment generating function will be equal to the expected value of e to the power 0 times x. By definition, this is equal to the sum of the px, and that is equal to 1. All right, so that is the condition for the moment generating function. It must exist for any t, negative t or positive t, and when you substitute t equal to 0 within the moment generating function itself, then you should have an answer equal to 1. If the answer is not 1, then the moment generating function does not exist, or it's not a valid moment generating function. All right, then the next proposition for a moment generating function says if the moment generating function exists and is the same for two distributions, then the two distributions should be the same or are the same. So that is, the moment generating function uniquely specifies the probability distribution, and there's a one-to-one correspondence between distributions and moment generating functions. And we call this property the uniqueness property. So if I refer to the uniqueness property, or I say use the uniqueness property to derive the probability distribution, or to identify the probability distribution from a moment generating function, then you should be able to do that. All right, so since it says each distribution has its own moment generating function, you can never have two different distributions that have different that have the same moment generating function. So each distribution has its own moment generating function. Now let us consider firstly random variable x that follows a Bernoulli distribution, right? So suppose that random variable x is a Bernoulli random variable with PMF defined as px equal to 1 minus p if x is equal to 0, and p if x is equal to 1, and 0 otherwise. All right, so now let us derive then the moment generating function of random variable x. how are we going to derive it? So we will use the definition. Always start with the definition. The definition says the moment generating function mxt is equal to the expected value of e to the power tx, right, capital X there, which by definition is equal to the sum over all possible values of x of e to the power t small letter x times the probabilities, right? Now this is equal to, if I start with x equal to 0, I'll have e to the power t times 0 all multiplied by 1 minus p plus e to the power t times 1 times p. And now this is equal to e to the power 0 times 1 minus p plus e to the power t times p. Now anything to the power 0 is equal to 1. Good. So the moment generating function of a Bernoulli random variable is given as 1 minus p plus e to the power t times p. Or in other words, we could say the moment generating function of a Bernoulli random variable is given as the probability that x is equal to 0 plus the probability that x is equal to 1 times e to the power t. That is the standard formula for any Bernoulli random variable. Now let us consider example 3.27. In example 3.27, they tell us that random variable x follows a Bernoulli probability distribution, or is a Bernoulli random variable, where in this case we have here p0 as 1 divided by 3 and p1 as 2 divided by 3. All right. So how can we then derive the moment generating function given these probabilities of x equal to 0 and x equal to 1? So again, we will use the definition. Moment generating function of random variable x is equal to the expected value of e to the power tx, and this is equal to the sum of the product e to the power tx times the probability. This is equal to e to the power t times 0 multiplied by 1 divided by 3 plus e to the power t times 1 multiplied by 2 divided by 3. And so this is equal to 1 divided by 3 plus 2 divided by 3 times e to the power t. So again, we see that this moment generating function of x follows again this general structure, right? If x follows a Bernoulli probability distribution. So if random variable x is a Bernoulli random variable, then it means that it will have the moment generating function p0 plus p1 times e to the power t, times e to the power t. So if you're just given, for example, a moment generating function of y equal to, let's say, a half plus a half et, then you should be able to give me the PMF. So you should be able to define the PMF as well as the probability distribution of random variable y just by looking at the moment generating function. This is what we call the uniqueness property, that the moment we know the moment generating function of a particular distribution, we should be able to recognize then the probability distribution from that moment generating function. All right, so in this example here, moment generating function of random variable y, if it's equal to a half plus a half et, then it means that y, in this case, will take on values 0 and 1, where the probability of y is, when y is equal to 0, it's equal to a half, and probability that y is equal to 1 is also 0. It's equal to 0.5 or half. All right. Now, example 3.28 says, let X be the number of claims in a year by someone holding an automobile insurance policy with some company. The moment generating function of this random variable is given as 0.7 plus 0.2 times e to the power t plus 0.1 times e to the power 2t. So from this moment generating function, we need to define the PMF of random variable x. So we will use our moment generating function to get the PMF. We will firstly follow the definition of a moment generating function. It's equal to the expected value of e to the power tx, and this is equal to the sum of e to the power tx times the probability, all right, for all values, possible values of x. So we need to identify here this pattern of a sum of e to the power tx times the probability of observing those possible values of x. All right. So if in this case we have here the sum of e to the power tx times the probability, if that is equal to 0.7 plus 0.2 e to the power t plus 0.1 e to the power 2t, then we can identify, or we can rewrite it as 0.7 times e to the power t times 0 plus 0.2 times e to the power t times 1 plus 0.1 times e to the power t times 2. All right. So from this, we can identify the possible values of our random variable x. That x, or random variable x, has possible values 0, 1, and 2. Alright, so we have the first row here. Possible values of random variable x is 0, 1, and 2. Now, what are the possible, the corresponding probability values? So px in this case, when x is equal to 0, is given as 0.7. When x is 1, it's 0.2. When x is 2, it's 0.1. So we have then the corresponding probabilities as 0.7, 0.2, and 0.1. All probabilities are positive, all right? And if you add them all up, 0.7 plus 0.2 plus 0.1, we get a total probability of 1. Good, so we can define here the PMF of a random variable just by looking at the moment generating function. Okay, then the next slide, we will be looking at how we can use the moment generating function to actually produce these moments. All right, so remember we said we would like to use the moment generating function to actually generate or calculate these moments for us. Okay, so there are two ways. One, we can use a formula or a theorem that says if the moment generating function exists, then the rth moment about 0, that is the expected value of x to the power r, is equal to the rth derivative of our moment generating function when t is equal to 0. So the expected value of x to the power r is equal to the rth derivative. So you derive the moment generating function r times, and then at the end you substitute t equal to 0. So what does this mean? It means that the first moment, expected value of x, is equal to the first derivative of the moment generating function. After you derive it, then you substitute t equal to 0. The expected value of x squared is equal to the second derivative of our moment generating function. So you derive your moment generating function twice, and then at the end of that derivative, you substitute t equal to 0. The third moment, expected value of x to the power 3, is the third derivative of our moment generating function. And after you derive it 3 times, then you substitute t equal to 0. And so on. and the expected value of the rth moment about 0, or expected value of x to the power r, that is the rth derivative of a moment generating function. So you derive your moment generating function r times, then at the end you substitute t equal to 0. The second way of obtaining moments from our moment generating function is by using this function here. Rt is equal to ln of the moment generating function of random variable x. So if we use in this function here and we derive it for the first time and substitute t equal to 0, then that answer will give us the expected value of x. If we derive then r the second time and substitute t equal to 0, then that answer there will give us the variance. Alright, so again, you can define a function r which is equal to ln of mxt. So it's ln of a moment generating function. And so the first derivative of rxt when t is equal to 0. So you firstly derive the function and then you substitute t equal to 0. That answer will be the expected value of x. Then the second derivative, if you derive it again, then you get the second derivative of rxt. Then at the end, substitute t equal to 0. Then that answer will be the variance of random variable x. Alright, so now we're going to prove the theorem as well as this second method here. That is actually true. So we will prove this by mathematical induction, meaning we will prove that the theorem is true for r equal to 1 and r equal to 2. And if you repeat the process number of times and do it by that's what it means by mathematical induction. You repeat the process r equal to for 3 and 4 and 5 and 6 and 7 or a number of times, then you will get for a general case which will prove that the theorem is true. Alright, so let us start with the first general case. So we are proving this here, that the expected value of x to the power r is equal to the rth derivative of a moment generating function when t is equal to 0. Okay, so let us start with the first one. So let us differentiate then the moment generating function the first time and let us see what we get. If we differentiate the moment generating function the first time, by definition, we have here the derivative of the expected value of e to the power tx, that is equal to the derivative of the sum over all possible values of x of e to the power tx times the probability, right? In mathematical terms, we can exchange the summation sign and the differentiation sign. And so we'll say this is equal to the sum over all possible values of x of the derivative of this product e to the power tx times px. And what are we deriving with respect to? We're deriving with respect to t. Do you see? Right, so a common mistake that students make is that they derive with respect to x. No, we're deriving with respect to t. Now this is equal to the sum over all possible values of x. If you derive an exponential function, so on the side here, if you derive this function, let's say e to the power 2w, this is equal to the derivative of the power, which is 2, times the function e to w. Now then this is equal to x times then the function e to the power tx times px. Alright? Okay, so now next, once we have then derived the moment generating function, we need to substitute t equal to 0. So when the derivative now, since we know that it's equal to the sum of x times e to the power tx times px, we can substitute t equal to 0, and now this is equal to the sum of all over all possible values of x times e to the power 0 times x times px. Now this is equal to the sum of x times 1 times px, right? Since anything to the power 0 is equal to 1. And now we have the sum of x times px over all possible values of x. This is equal to, by definition, this is equal to the expected value. So this is equal to ex by definition. So we proved that expected value of x now is actually equal to the first derivative of a moment generating function when t is equal to 0. Now let us do the proof then for expected value of x squared. So we need to derive then the moment generating function for the second time. So if the moment generating function is equal to, or the first derivative is equal to sum of x times e to the power tx px over all possible values of x, then the second derivative, or if we derive this again for the second time, then that is equal to the derivative of the summation of x times e to the power tx times px. Now mathematically we can interchange the summation sign and the differentiation sign, and so this is equal to the sum over all possible values of x of the derivative of x with, so we're deriving with respect to t, all right? So we're deriving x times e to the power tx times the probability of x. Now this is equal to the sum, again, of all possible values of x. What do we do with the power here? The derivative with respect to t then is equal to x times e to the power tx times the probability. This is equal to the sum of x squared times e to the power tx times the probability. We're summing over all possible values of x. Now, if you substitute t equal to 0, then it means that the second derivative of our moment generating function will be equal to the sum of all possible values of x squared times e to the power 0 x times the probability. By definition, this is equal to the expected value of x squared. And so we have proved then that the expected value of x squared is equal to the second derivative of our moment generating function when t is equal to 0. Now if you repeat for, let's say, k equal to 3, 4, 5, 6 until some rth number, until r, we will see then by mathematical induction. So if you do this for number of times, then the proof will exist, or it will be true. So if you repeat by mathematical induction, it will be true that if you derive the moment generating function our number of times and substitute t equal to 0, then that derivative there will be equal to the expected value of x to the power r, or the rth moment about 0. Now let us then prove that if rxt, so here we're proving if we have a function rxt equal to ln of the moment generating function of a random variable x, then the first derivative of this function r with t equal to 0 is equal to the expected value of a random variable x, and the second derivative when t is equal to 0 is equal to the variance of a random variable x. So now let us prove that. Okay, so we will start firstly with the expected value, all right? So you start with what you have, and what you have is the function. Rxt is equal to ln of the moment generating function. Now the first derivative, and we're deriving with respect to t, so the first derivative of this function is equal to the derivative of ln of mxt, all right? And we know that if we have a function ln of fx, or ln of, I'll say fw, then the derivative with respect to w of ln of fxw is equal to, so you have then fw in the denominator, and then in the numerator you have the derivative of fw. All right, so now the derivative of ln of the moment generating function is equal to, so in the denominator I'll have the moment generating function, and in the numerator it is the first derivative of the moment generating function. Now we can substitute. Now for t equal to 0, the derivative, or the first derivative of this function rxt, is equal to, so now we're substituting t equal to 0. So we have the first derivative of the moment generating function when t is equal to 0 divided by the moment generating function itself when t is equal to 0. Now in the previous theorem we proved that the numerator is equal to the expected value of x, right? And then the denominator is equal to what? So it's equal to, I'm gonna scroll up quickly. Okay, so I'm gonna scroll to this property here that says a moment generating function exists for when t is equal to 0, then the moment generating function is equal to 1, right? Okay, so now we have here, we're assuming that we're using a valid moment generating function here, and we're just proving that the first derivative of this function rxt is equal to the expected value. So the denominator here is equal to 1, and so we could see that the moment that the first derivative of rxt is just equal to the expected value of a random variable x, which is also equal to mu. Okay, so now let us prove then that the second derivative when t is equal to 0, let's prove that it's equal to the variance. All right, so the first derivative then of rxt is equal to the first derivative of moment generating function divided by the moment generating function itself. Now if we derive then the function rxt for the second time, then we're looking at the derivative of mxt, right? Mx prime t divided by the moment generating function itself. Well, we will use which rule here? So in calculus, already you should know the quotient rule. And so the quotient rule says the derivative of the function hw divided by fw is then equal to, in the denominator you have fw squared the numerator you have fw times h prime w minus hw times f prime w. Okay, so we could see that this is in this form here of a fraction, and we're deriving with respect to t. Now this is equal to, this derivative is then equal to mxt all squared, right? Numerator, then I write down mxt here, times then the derivative of the numerator there, mx prime, which will be the second derivative now, minus, then I write down the numerator function again, times the derivative of the denominator here, which is mx prime t. Now this is equal to mxt, the moment generating function, times the second derivative of the moment generating function minus the derivative of the moment generating function squared, okay, all divided by the moment generating function squared. So this is the second derivative of your function rxt. Now if you substitute when t is equal to 0, the second derivative will then be equal to, so let us substitute then t equal to 0. I have in the numerator mx, okay, when t equal to 0, times then the second derivative when t equal to 0 minus the first derivative when t equal to 0 squared divided by the moment generating function when t equal to 0 squared. Now this is equal to, in the numerator we said that that expression there is equal to 1, alright, multiplied by the second derivative, and we said that the second derivative is equal to, we actually proved it in the previous theorem, in the theorem we proved that the second derivative when t equal to 0 is equal to the expected value of x squared, right, minus, then we said that the first derivative of a moment generating function when t is equal to 0 is actually equal to mu, right, then we square that, and the denominator, this expression here is equal to 1. And so we see that the second derivative of our function rxt when t equal to 0 is just equal to the expected value of x squared minus mu squared, and by definition this is equal to the variance of random variable x. Alright, now we have a proposition on a linear function of random variable x. It says there that let random variable x have a moment generating function mxt there, and let y, random variable y, be equal to ax plus b. Then the moment generating function of y will be equal to e to the power bt times the moment generating function of x, where instead of t there within the brackets we have at. Alright, let us prove this. Okay, so if y is equal to ax plus b, where a and b are constants, remember, then the moment generating function of y is by definition equal to the expected value of e to the power ty. Isn't that true? Okay, now this is equal to the expected value of e to the power tax plus b, right? This is equal to the expected value of e to the power a tx plus tb, and that is equal to the expected value of e to the power atx times e to the power tb, right? Since e to the power a plus b is equal to e to the power a times e to the power b. Now this is equal to e to the power tb. Then I'll just take out the constants or anything that's not linked to our random variable x. In this case, it's e to the power tb times the expected value of e to the power atx. And so, by definition, if the moment generating function of x is equal to expected value of e to the power tx, where we have there t in front of the x, then it means that the expected value of e to the power atx, now if you look at at as one entity, then that is equal to the moment generating function of x in brackets, then you have at. Alright, so now this is equal to e to the power tb times the moment generating function of x. Within the brackets you have at.